I am Mary Beth Lachak. I am the Director of Strategic Communications at the Canada-France-Hawaii Telescope. And I have a bachelor's degree in astronomy and astrophysics from Penn State University. And then I went back and got a master's degree in educational technology in 2000. I think I graduated with that in 2010. I actually did that while I was working here in Hawaii. So I was apparently a trendsetter in online learning without really even realizing it. I've never been to San Diego State, where my master's degree is from. I essentially describe my job as talking to people about space. So I just came from talking to third graders about the solar system through one of the events that we've organized during COVID. And now I'm talking to you all about the Canada-France-Hawaii Telescope, astronomy at the top of the world. So I always like to include a map because I'm almost never near the people that I'm giving talks to. And if I have flown somewhere and I'm giving a talk, I do like to then just show how far I've gone. 9 hours, 5 minutes is not a bad flight. I feel like that includes some drive time from Philadelphia, because my assumption would be I'd fly into the Philadelphia airport and then drive to Hazleton. This is the Canada-France-Hawaii Telescope. And so this is the facility that I work at. It's a almost 42-year-old facility located on the summit of Mauna Kea, which is a roughly 14,000 foot extinct, a dormant volcano in Hawaii. My offices are in Waimea, and that is where I live now. I'm not far from, I live like a mile from the office. I'm actually working at home still. Due to COVID and COVID protocols, we are still having most staff that can work from home. The exception is if you got to go up there, you have to go up there. So, and this is our summit facility. We have, I would argue, the best site on the best mountain in the world. All of our observations are actually taken from Waimea. My first job at CFHT was to take observations. And so I have worked about 600 nights at the summit, working with one of the cameras that we have at CFHT. And that was from 2003 to about 2010. When I was up there, we had two people, one person who took care of the instrument, and that instrument then sent commands to move the telescope. And the other person was responsible for the building. We've actually been able to take all of that remote and bring it to our remote observation room in Waimea. It's more cost effective. You have more air. So those of you, and I know a couple people mentioned it, those of you that have been to the summit of Mauna Kea, or really any volcano or any mountain, the higher you go, the less oxygen you have, the less you think clearly. I like to say being at the summit of Mauna Kea is like having 2 glasses of wine on an empty stomach. Your edges start to feel a little fuzzy. One of my coworkers mentioned that when I was talking to him, that he often he's a notepad in his coveralls, because that way he can write down exactly what he needs when he goes from the telescope on the 5th floor down to the machine shop, without having to radio somebody that he needed it. It's a very rarefied air environment. All right. So why Mauna Kea? Why is there a facility, a group of facilities on the summit of this volcano in Hawaii? It's the best site in the world for astronomy. Now, before I hear in the comments about Chile is a simply phenomenal site. I would put the best night against Mauna Kea against the best night in Chile, and I would win. Chile does have more clear skies, more nights of cloud that are cloud free, but for the reasons that we're going to talk about here, the site conditions aren't the same quality as Mauna Kea. It's the second best site in the world, and there's nothing wrong with being the second best site in the world. Hawaii in Mauna Kea has a very dry atmosphere above it. If you go to the summit, I have been up there on nights when there's 10% humidity. And so because we have such dry air, and there's actually one of the facilities, the James Clerk Maxwell Telescope, one of the measurements that they take on a nightly basis is of the moisture in the air. They are a microwave facility. And so with that, when the light from, as you all know, when the light from space enters, when we don't have that moisture, we see less twinkle in the stars, and we get a clearer image and a better image quality. It's usually cloud-free. This week we've had 2 days of snow at the summit. We just got a dusting. Usually it can snow year round. The ambient temperature of the summit is somewhere between freezing to about 50 degrees, depending daytime, nighttime. This year we have seen it get really fairly cold. For Hawaii, it has gotten into the upper 20s at the summit this year. I think the warmest that I've ever been up there is about 54. So we don't have a huge swing in temperatures there. So it can snow year round. When we see the most snow is the winter months, simply because of weather patterns in the central Pacific. This is when we have in Hawaii basically our wet and our dry season. So right now we're coming out of our wet season. We're entering a drier spring. I think March was one of our rainiest Marches on record, at least for my friends in Hilo. But the summit is clear and often above that. We have a very stable atmosphere. We are surrounded by thousands of miles of the Pacific Ocean in all directions. And so for the first probably decade that I lived here, I only saw a handful of thunderstorms. And you kind of compare that and contrast that with the weather conditions that we would see in Pennsylvania, where we get particularly in the summer months, we get those thunder clouds that roar due to the differences in heating and cooling between the land and the sky. We have a very stable atmosphere above Hawaii. That's why if you fly in, we very rarely have turbulence flying into the Big Island. We have very few city lights. The Big Island is a very rural community. We have a population of about 200,000 people. The town of Waimea that I live in has about 10,000, maybe 12,000 people. We have 3 red lights, and most of the street lights that we have are only at the intersections where you truly need them. We also have a very good relationship, astronomy in Hawaii, with the county lighting departments. And so if you come to the Big Island, you will notice we have 2 colors of street lights. One is a sodium vapor that is an orangish red. Those were our older street lights. For cost saving measures and longevity, they've moved to LEDs. However, the LEDs are fully shielded in the blue. So all of our street lights are kind of a greenish yellow, eerie. All of the lights point down, unlike where we see lights in a lot of urban places where you see the light pointing upwards. It's not illuminating the ground below you, but the sky above. And so we have I think the Big Island has the second strictest lighting ordinances in the state. The strictest is the island of Kauai because of their rare endangered bird sanctuary on the northern part of the island. There were some bird accidents, and that's why their rules are a little stronger than ours. Finally, the atmosphere at the summit is dry and clean due to the inversion layer. So oftentimes, if you see a picture of Mauna Kea, you see that there is either, if you're a picture at the top, like I showed you of CFHT, we see a cloud layer below. If you're actually looking at the mountain, it's not uncommon to see it bisected by a cloud layer. That's due to the inversion layer. So that dry, clean air from the upper atmosphere interacts at somewhere around 6,000 to 10,000 feet with the tropical air of the lower atmosphere, and we get a cloud layer. As long as that inversion layer is below the summit, that tropical moisture that one would associate with Hawaii is kept much lower. That's also where if Kilauea, our volcano, is erupting, the vast majority of the pollutants on the Big Island are from the volcano. And when it is erupting, those pollutants are also kept, for the most part, below the summit level. The shape of the mountain is also important. So Mauna Kea and all of the volcanoes in Hawaii were formed over a single hotspot. And as the plates moved away from that hotspot, that's where we see the development of the island chain. This means that we have a very smooth shape to the mountain, as opposed to mountains that are formed through plate tectonics, where you see the actual physical crashing of plates together. So this gives us a really gentle laminar flow over the summit and over the summit conditions. that contrasts with areas where you would have, sort of a roiling wind as the wind comes through and hits the jagged peaks of mountain ranges like the Andes, the Alps, or the Rockies. This is an image taken by a student of the Milky Way from the summit. This is obviously a bit of a low light level camera that she exposed for an extended period of time because we can see the moon here. But you can see this is the Milky Way. Mauna Kea is actually one of the darkest places on Earth. When we look at northern latitudes and think of places like Denali, we would think of them as darker. However, they end up with more auroral glow, contributing to a brighter overall sky background than we have at the summit. This is us. We are 40, soon to be 42. And this is a time lapse of the beginning of night preparation. So what you're seeing here is our shutter open. That process takes about 8 to 10 minutes and is akin to a garage door opening. What I want to highlight here on the sides are these labeled we can see R6 through 3 here. These are our louvers. They were retrofitted about a decade ago. And the problem that we're having is that all of the warm air was rising directly above the top of the dome, which is causing what we refer to as the chimney effect. So where we should have had the best image quality at the start of the night was not. So we had the idea to cut holes in the dome, and you'll see this actually, you can see it open on the side, and install louver windows. So these dome vents actually cross-ventilate the dome, clearing it out of warm air and allowing us to be able to observe at the start of the night directly overhead. I'm actually gonna, when this finishes, go back a little bit. I was talking about our vents. At the beginning of our night, we move the telescope to the east, so we're able to flush out the dome more effectively without worrying about the sun. Now we see at the top here, this is MegaCam. This is going to be the first instrument that we talk about. MegaCam is our wide field optical imager. It takes a picture on the sky of 1 degree field of view. And here is our mirror. We have a 3.6 meter mirror. We re-illuminize that mirror every several years. We actually just had our last re-illuminization in October. So this is my coworker, Tom, taking what he calls a high altitude selfie. He's standing at the very top of our dome. What he was actually doing was up there doing a 360 panorama image for a project that we were working on at the time. Behind him, we can see some of the Mauna Kea observatories. This is the Caltech submillimeter observatory. It's currently in the process of being decommissioned. Caltech decided that they wanted to use the funds for CSO in other areas. Behind Tom is the James Clerk Maxwell telescope, and directly behind his head is the submillimeter array. These two facilities operate in the microwave. So JCMT has a 15-meter collecting dish, and the submillimeter array is made up of 8 smaller dishes that can be moved around in different configurations by heavy mechanical equipment to either image close to get higher resolution or lower resolution, depending on the project. The 2 of those facilities were 2 of the 8 involved in the Event Horizon telescope that imaged the black hole at the center of M87, which we'll talk a little bit more about later. Over here is the Subaru telescope. It's the National Telescope of Japan. You will notice that it has a different shape. It was built in the late 90s, and as opposed to the traditional dome shape, they went with wind testing to show that you get less disruption of airflow when you have a dome of that shape. The problem is that it snows in Hawaii, and occasionally they end up with snow on the flat surfaces of their roofs. Here we have the twin Keck observatories, arguably the most famous facilities on Mauna Kea and perhaps in the United States. They are 2 10-meter mirrors. Subaru is an 8. These are segmented mirrors. Subaru is solid glass. Here's the NASA Infrared Telescope facility. It operates in medium infrared, the mid-infrared wavelengths, which is why it's open during this image. I don't know exactly what they're imaging, but if you made me guess, I would say something in our solar system. They often do daytime observations of planets, comets, and asteroids during early morning or late afternoon. So let's talk about our science. So as I mentioned, I'm going to talk primarily at first about our MegaCam, our imaging capabilities. So this is our very first image ever taken in 1979. This image was taken on August 7th. It was a very big deal because the International Astronomical Union was having its triannual meeting in Montreal. And so obviously the Canadians kind of wanted to show off from their new telescope and their new telescope facility. And this is what we can do today. And so I know what I am doing by showing you this picture. This is a simply stunning image. I can't even be like, there's no humility. This is an amazing image. I had very little to do with that, because this is a perfect representation of how, as a 40-year-old facility, we are still consistently ranked as one of the most scientifically productive facilities on Earth. So this is an image from two of our PIs, Alan Duke and Jean-Charles Couillon. So Jean-Charles used to be one of our resident astronomers, and this image is of Stephan's quintet. And so this is a combination of observational technique and data reduction to give us what we call low surface brightness mode. And so what Duke and Couillon were looking at is actually intergalactic cirrus. So they were doing observation of the gases that exist in between the galaxies and the extended halos of the galaxies in Stephan's quintet. With this, it gives us that, that truly unique viewpoint on seeing the intergalactic cirrus between them, combined with the fact that we do get a lot of information about the extended halo. Now, Jean-Charles does our annual calendar, so he has taken this from a science image to an artistic image. And I say that not because this isn't a true representation of what the astronomical data looks like, but Jean-Charles knows how to, when you've put your blue filter in, he knows what shade of blue looks best and what shade of blue goes best with the yellows and the reds. This is at least 21 images reduced and stacked. And I would actually wager a guess with that level of intergalactic cirrus that this is considerably more than that. This was one of the first legacy projects that CFHT had with MegaCam. This looks like a blank field of view. This was one of our deep survey patches from our Canada, France, Hawaii telescope legacy survey. And so as we zoom in on the deep, we start to see fewer and fewer stars and more galaxies. And if we go all the way into this montage of galaxies, we can see essentially a large part of the history of the universe. So here with our nice barred spirals, we're looking at galaxies that are very close to us. The redder and yellow galaxies have been redshifted, and their light is much more distant. Now, one of the science goals of the DEEP survey was to look for type 1a supernova. So type 1a supernova occur with a very, very specific mechanism. When our sun reaches the end of its life, right now it's in perfect balance. Gravity pushes downward, pressure pushes outward, and they're in balance. At some point, the core of stars like our sun will run out of hydrogen to fuse into helium. Their energy production will decline and their radius will shrink. Eventually, that triggers more fusion in the core, a helium fusion. The star puffs out, leaving us those beautiful planetary nebulae that I'm sure you've all looked at in your own telescopes, and a white dwarf core. Now, if that white dwarf core has a companion binary, it can accrete, it can pull matter from that binary and actually increase in size. Now, there's a very firm limit, 1.44 times the mass of the sun, known as the Chandrasekhar limit. When a white dwarf surpasses that limit, it explodes in a type 1a supernova. Because the mechanism for the supernova is always the same, they work as standard candles, allowing us to be able to measure distances. They have a standard brightness, measure distances back in time. And so when we talk about space, distance and time are very closely linked, as you all know. So the type 1a supernova that were detected, about 504 of them during this deep survey, were additional data that led to the confirmation of the expansion of the accelerating universe, which won the Nobel Prize in 2012. By measuring the distance to these supernova and these galaxies, they were able to more accurately constrain the acceleration of the universe. This is another example. So this is another survey that we do. It's kind of a survey. We do it during bad seeing. So anytime the seeing's worse than about 1.2 arc seconds. One of the programs that we work with is called Pristine. And so what Pristine aims to do is look for the very oldest stars in our galaxy. So this is the star itself. What they do at CFHT is they take an image using our CAHK filter and look for stars that are either disappear or significantly dimmed in that specific filter. So they can then do follow-up, spectroscopic follow-up, and get results like this. So we see the Pristine, I'm just calling it Pristine instead of all of its letters. The Pristine star here, we see that it has almost zero metallicity as compared with to the sun. We see a handful of hydrogen lines. Maybe we see a little bit of the calcium here, but otherwise it's a much flatter spectrum. This tells astronomers that this is a very, very, very old star. I don't remember the age of the star off the top of my head, but this is what the Pristine group aims to do. And because they don't need the best image quality, they're able to get a considerable amount of data by operating in what we deem suboptimal conditions. Sorry, Paul, forgot to fix the GIF. I meant to do that between the Pittsburgh talk and this talk. What you should see is the discovery images for a dwarf planet named RR245. So one of the other large programs that we ran at CFHT from about 2008 to I want to say 2012 was AUSIS, the Outer Solar System Origin Survey. So the AUSIS team looked at 4 patches of the sky trying to detect icy bodies past Neptune. This one here, RR245, falls into the category of dwarf planet. We can see it's exceptionally extended and elongated orbit here. It is a circular object and it does orbit the sun, as we see. We caught it on the close approach. If it had been either coming in or going out much farther, it would have been very difficult to detect. So the AUSIS team found about 804 of these objects during their survey, looking at just 4 patches of the sky. What I like to highlight in this mess of graph is we can actually see this gap right here. This gap is caused by the gravity of Neptune. Often when we think of gaps, we think of the Kirkland gap in the asteroid belt caused by the resonance frequencies with Jupiter. And we see a very, very similar thing here with Neptune. It's much preferred for this 3. We see many more objects in this 3-2 resonance with Neptune, or some of the farther backs than we see in any of these gaps that exist. So the AUSIS team has waded into the discussion about Planet 9. Now, you may be familiar, Mike Brown from who has used the Keck Observatory. So Mike Brown and his team did a 60 Minutes interview a couple years back where they talked about how their theoretical modeling shows that we need to have an object of sufficient mass out in the solar system that we've yet to detect, Planet 9, that can account for some of the gravitational wiggles that we see in some of the orbits of the outer planet. The AUSIS team disagrees with that. They feel that from their small sample, 804 over 4 patches, that there's actually a vast number of to date undiscovered objects that combined mass could cause that same perturbation that we see in the orbits. I think the best example that I've heard of this is something that will all resonate with you guys in Hazleton. If you're driving along the road, you see the deer on the side of the road, but you miss all of the deer that are in the woods. So what the AUSIS team advocates is that they are only detected the deer on the side of the road, and we are missing a vast herds of deer deeper and deeper within the forest, i.e. the Kuiper Belt. On the Big Island here, we do not have deer, but we have a lot of goats and bighorn sheep. So the analogy works the same. You get deer, the Canadians get moose, I get goats. This is another one of the projects that I really think is fascinating. This is M31 and M33. You'll notice that the headline for this is in French, Canada, France, Hawaii telescope. If we look here, this is the area of Andromeda that is typically imaged. What this team, and similarly for M33, what this team did was they wanted to look at the extended halo. This was part of the Pan-Andromeda Archaeological Data Survey, or PANDAS. And so what they were studying is the extended halo of both of these objects to look for evidence of galactic cannibalism and dwarf planets that may, or not dwarf planets, dwarf galaxies that may have been ripped apart by the immense gravity of Andromeda and M33. And so that kind of information provides us insights into the galactic halo of our own galaxy, of which we will talk about in a minute or two. And I will mention another one of our big discoveries towards the end. WeirCam is our wide field infrared camera. It came on sky in 2006 or so. It was cutting edge infrared technology at the time. We still use it an incredible amount for a variety of projects. This is my default slide of why do we even look in the infrared. You're all familiar with the optical image there of the Orion Nebula. And then the image to the other side is the infrared image of that. We're able to see through all of the cold gases and really drill down to the star formation that lies a little bit deeper within. Looking at the infrared unlocks areas of star formation. It also gives us the opportunity to study brown dwarfs, look for planets to a certain extent, and look for very, very distant objects. So this is one of my favorite news releases that I've ever worked on. Strategic communications. I work with all of our astronomers user community on their news releases. Generally, they come to me with a draft, and then I edit that draft and make it readable for the average person who's clicking on our news site and keeping the essence of what they want to do. So this discovery was made by Trent Dupuy and Mike Liu. They were, Mike was Trent's graduate advisor when he was at the University of Hawaii at Hilo. Trent then did a postdoc. He then worked at Gemini. He's now in Edinburgh, and he and Mike still work together. They spent over a decade studying the same 36 pairs of brown dwarfs. So brown dwarfs are, many people think of them as failed stars. I like to think of them as very successful planets. To be a star, you have to have that sustained fusion. Brown dwarfs sort of flicker in and out of fusion. They are larger than planets, roughly about 70 times the mass of Jupiter or so is sort of that cutoff limit. Now, what Mike and Trent were looking at here is this object 0557AB. That is a binary brown dwarf pair that are orbiting each other. They then discovered the smaller object 0557C, a planet orbiting this binary brown dwarf pair. And this planet ends up being a doppelganger of one of the sort of prototypical planets that we see out there, Beta Pictoris b. So it was a really fascinating conversation because they weren't quite sure what to call the little guy, C. Was it a planet? Was it an object? Could we really put a planetary label? What was its mass? Is it close enough? They eventually settled on planet. And part of that was my indication of, well, it's a lowercase level, guys. People are going to ask lowercase letter. People are going to ask questions. The same combination also discovered a rogue planet. So this is a planet that has been tidally stripped from its host star. It has one of the NASA Travel Bureau exoplanet posters. It's PSO and then a string of letters and numbers. That was discovered by Dupuy and Mike Liu. Espérance is our spectrograph. So both one of our spectrographs. So with Espérance, with WeirCam and MegaCam, we're looking at very large fields of view on the sky. As I mentioned, MegaCam is a 1 degree by 1 degree imager. Espérance is the opposite end of that extreme because it is a spectrograph that looks at the light from a single star. Now, what makes Espérance unique is that not only does it look at the spectra, but you're also able to get a detection of the magnetic field of the object by using it in its spectropolarimetry mode. And this is Espérance hanging off the telescope. These fibers go all the way down into the actual spectrograph, which is housed on our 3rd floor in our inner coude. This is not a spectra from Espérance, but what the team led by Rodrigo Abada did was they used Espérance to take spectra of 5 or 6 stars that were part of a stellar stream. Now, their hypothesis was that Omega Centauri is not a globular cluster, but rather the remaining core of a dwarf galaxy that's been galactically cannibalized, tidally stripped by our Milky Way. So what they discovered is that there's actually a bit of a tidal tail coming down out of Omega Centauri. And they used Espérance to take spectra of these stars along the stream. And with that, they were able to determine that the composition and the velocity of those stars were identical to the composition and velocity of Omega Centauri, leading them to hypothesize, not saying theorize yet, hypothesize that this was in fact a tidal stream, and more research needs to be done into Omega Centauri, globular cluster, dwarf galaxy core. This one always runs before I'm ready for it. So our next instrument that I'm going to talk about is CTEL. CTEL is an imaging Fourier transform spectrograph, an imaging FITS. It takes a picture of space, and I think it's 11 arc minutes by 11 arc minutes. And then through the magical hand-waving math that is Fourier transforms, it converts that information into a spectra for every pixel on the camera. So we end up with 4 million spectra per CTEL image. This allows us to create a 3-dimensional map of the area that we're looking at. This that I'm going to show you here is a galaxy. And as we kind of flip through this data cube, it's exactly like watching a movie. We will see how this galaxy looks at different, very specific wavelengths, which gives us an indication of what's going on in the center of the galaxy. So we'll watch and then talk. So what we're seeing there is highly ionized gas emanating out of the core of this galaxy. Hypothesis is black hole. So you've got a black hole that is in the core of this galaxy. And when we think of black holes, and I just had a very long conversation with 3rd graders about them today, we often think of them in a 2-dimensional way. You have objects that are orbiting around them, and then those objects either fall in. We need to think of black holes as 3-dimensionally because they have intense magnetic fields in the accretion disk, cause of quasars. And so what we're seeing is the supercharged, superheated H-alpha gas emanating out of the core of this galaxy as it's superheated by the black hole in the very center. So when we're getting to this part here, I will play it again. Oh, come on. Okay. We start to see those supercharged, superheated gases. And so Mari Liu, who actually was a graduate student while working on this, now works at OMA. And so she's continuing the research into these galactic areas. If you go to our website, there's actually a really phenomenal video in our news section. I think it's called the Heart of the Crab Nebula, that is in fact a 3D mapping of the Crab Nebula done by the CTEL team. I'll incorporate that into future PowerPoints probably. Our last instrument to talk about is SPIRU. So SPIRU is our infrared spectrograph, similar to Espidon's in that it's also a spectropolarimeter, but it is a high precision velocimeter. We're hoping to get down to about 1 meter per second detection of radial velocity. So oftentimes when we think of gravity, we think of the impact of a star on a planet and not the inverse, the impact of a planet on a star. And so what SPIRU does is it looks for the gravitational wiggle, the perturbations caused, inflicted on a star by its orbiting planets. So this is AU-MIC. We can see an image here of the transiting planet. So SPIRU did a spectroscopic follow-up to NASA's TESS mission. So TESS looks for transits. So if I am a star and my phone is a planet and it passes in front of me, my light is being dimmed the entire time that it passes in front of the plane of the star, and then my light shines again. There are a lot of things that can cause that dipping in light. So when these objects are detected previously by Kepler, now by TESS, spectroscopic follow-up on Earth is needed. And that is what SPIRU did here. So they looked at AU-MIC, which is a very young star, about 22 million years old. Young stars tend to be highly active. They have very energetic magnetic fields, lots of star spots, lots of coronal mass ejections, as you can see illustrated in another NASA exoplanet poster. I'm very proud when our objects get exoplanet poster status. I feel like it's, you know, like you've made it a little bit. Super cool discovery. And so what the team not only had to detect the wiggle from a planet in its star, but also they had to remove all of the perturbations caused by the stellar activity. So if we look here, this is a plot of the stellar rotation period, and we see the little bump that's the planet orbit. And if we come down here, we actually can see the planet a little bit more. So with the TESS observations, they were able to determine the radius of the planet. With the SPIRU observations, they were able to determine the mass of the planet. Mass and radius gives us a density. So what you're looking at here is essentially a hot Neptune. It is larger than Jupiter, so I guess it's a hot Jupiter. It's a hot Jupiter with a density of Neptune. The reason that this is a critical observation is that this is, again, constraining even more planetary formation models. So for a planet Jupiter-sized and larger to form, it has to form in cooler areas of the stellar nebula, the star formation region, past the frost line, which is, if we imagine, is about halfway through the asteroid belt here on Earth. However, we have discovered a lot of hot Jupiter-sized planets that orbit closer than Mercury. At some point during the formation of these star systems, the gravitational pull, something causes that Jupiter-sized planet to move from its outer solar system much closer to the inner solar system. By seeing an observation like this in a planet this young, that also really, like I said, constrains the age in simply 22 million years. Sorry, my cat's very grumpy because she had to face the indignity of going in the cat door instead of being let in. So if you hear sad meowing, sympathy ploy, just ignore it. It really constrains that. Not only did the planet form, but it also migrated in that 22 million year period. The bulk of the work that I do, as I mentioned, does involve our community engagement. So my work on the science side is telling the stories of the scientists that work at CFHT and the research that we do and the observations and the discoveries that we made. A lot of my work is sharing astronomy with the community in general. So this montage I created for our board of directors meeting a couple years back. It's kind of jarring now to see all of these people like close together and unmasked for me. Like, what is even going on here? But I assure you, this was pre-pandemic. So every year I have to write a report to our board of directors, and then give a presentation a couple weeks later. This was everything that we had done in that couple of weeks. So we had hosted a star party, which is something that we do annually. We did host our star party virtually this year. I can put a link in the chat when we're all done. And what we did for that one was we took the event and we made it virtual. We took all of the different aspects and made a video, separate videos. So one of my coworkers, Mark, who's also an amateur astronomer, he did a whole video on, so you think you want to buy a telescope, you really want to buy binoculars, because let's make sure that you think you're interested enough in space to make the investment, because they're less expensive. It's a lower threshold for entry than buying a telescope. The next one was a tour of our remote observing room and a Q&A with one of our remote observers. We had a live question and answer with two of our astronomers, and it cultivated in what was supposed to be a virtual star party. It was more or less a virtual star party, but we ran into some technical difficulties. We were working with a team at the Mauna Kea Visitor Information Station at the 9,000 foot level. And pandemic, they hadn't really used their telescopes in a while. And so we ran into some technical issues even that occurred after our trial run. Good fun, all visible on our website. I run a program called Mauna Kea Scholars. I actually awarded telescope time this morning to a student. So it is a research opportunity for Hawaii public high school students to use the observatories to conduct their own astronomical research. And what really sets Mauna Kea Scholars apart from other programs is a combination of things. One, they can use the scientifically most productive facilities on Earth. I have a student that doesn't know it yet, but will be receiving Keck time on the Keck Observatory. They are very kindly taking some observations for me in twilight. So it's the sort of the gap when they normally wouldn't be doing observations. They have what they call their twilight zone observations. Now, I have had students get full-on Keck time for their own independent research, but I'm really taking advantage of some loopholes that I'm aware of. This morning, we awarded telescope time to a high school senior using the Las Cumbres Observatories, which is a series of telescopes, one on Haleakala, on Maui, and the others around the world. She wants to do some research into the habitable zone of Algol. I have a student on Molokai. She's a senior. She will be submitting her senior research paper to graduate with a STEM diploma. She has been studying the Horsehead Nebula for 3 years. Her first observations were submillimeter observations in the core of the Horsehead using an instrument called Scuba 2 so they could analyze the magnetic fields. And she now has the single most comprehensive data set in broadband and narrowband of the Horsehead Nebula ever taken. I know that because we saw something interesting and we tried to do a literature search, and no one else has ever looked at it with this specific filter. And so there's no literature search. Try explaining that to a 17-year-old who kind of freaks out a little bit because there's no answer to the question. These students are actually mentored by graduate students at the UH Institute for Astronomy. So the grad students review the paper proposals, help them refine them. My goal with this program is not to create a million little astronomers, but rather empower our local high school students with the idea that they can do STEM. They can be people who do STEM, and there are jobs back for them in Hawaii. I really run the gamut with students that I work with. These are all of the schools. For example, my students at Honokaa High School are an after-school astronomy club, similarly with Waipahu High School. That's not happening this year. The club rebooted and is very slowly having events, but they've just not had the capacity. I work with AP students. AP Research was the group that I gave telescope time to this morning. I work with credit recovery students. These are students that have not passed their requisite science courses by the time they are a junior and end up taking other science classes that they need to graduate. And so when you award Keck time to a student who has their entire life either felt or been made to feel like they're not smart enough, that is really mind-boggling. And that really changes their perspective of what they're capable of doing. I would love to see all of my Mauna Kea Scholar students come back and work at the observatories in a variety of positions, except the ones that want to be doctors, engineers, technicians. We at CFHT and all of the observatories, we obviously have PhD astronomers, but we also have community college dropouts who happen to be experts in how you use diesel engines. And so it's really runs the gamut. And that's what I want to open up for these students. Another program that we're exceptionally proud of is called Ahua Hea Noa, which means to call forth a name. And so Ahua Hea Noa began with Oumuamua, the object that you see on the right. Okay, it says Oumuamua. It's obviously labeled. I'm not good with left and right, and I'm even worse in this Zoom world. So Oumuamua was detected. It's the first interstellar comet ever detected. It was detected at first at Pan-STARRS on Haleakala. And this is one really great example of kind of how all of these different observatories work together. So the University of Hawaii at Manoa has time on all of the facilities, and they were using the Pan-STARRS telescope on Haleakala to look for near-Earth orbiting objects and other small icy bodies in our solar system. About 50% of all comets and asteroids are discovered with the combination of Pan-STARRS and CFHT. So our executive director received a phone call from Dr. Richard Wainscoat from UH. And Richard said, I have an object that I think is from another solar system. I need data, and I need data tonight. Okay, so we did the follow-up observations. Very rarely do we work with PIs, primary investigators, in real time. The closest we get is Richard. Megacam is on the telescope tonight. He and his team will likely send us an email at maybe 4 with a list of targets that they want us to do follow-up observations on. In this case, it needed to be done in real time because the object was moving so fast. So technology at its best, Richard was in the lobby of a hotel in South Korea, working with one of our remote observers and one of our resident astronomers to make sure that we got Oumuamua. Now, a couple weeks prior to this, a businessman named John DeFries, who's native Hawaiian, he's now in charge of the Hawaii Tourism Authority. He had come to my boss, Doug Simon, CFHT's executive director, and Kaiu Kimura, the executive director of the Amiloa Astronomy Center, with the idea that objects of note that are discovered in Hawaii should have Hawaiian names. And so they formed a working group, gave a presentation to all of the other Mauna Kea directors, and everybody's like, yeah, that sounds great. So this was late October, and the decision was made. November and December is everybody's busy season. You've got meetings, end of year meetings, that in January they would reconvene and really start this naming process. And then Richard called with Oumuamua, and Doug saw a loophole and an opportunity. There are no naming conventions for objects from outside of our solar system within our solar system. So Doug talked to Richard and Dr. Karen Meach, who was also a member of the team, and Dr. Rob Weck, who were part of the discoveries, and said, proof of concept, can we give this object a Hawaiian name? And Karen said, if you get me a name in 72 hours, it'll be in the Nature paper. So Doug called Kaiu and her uncle Larry, Dr. Larry Kimura, who's an expert in Hawaiian language. And Larry is one of the voices responsible for the resurgence of the Hawaiian language since the 1970s. And so he looked at it and he named it Oumuamua, which means a scout or messenger from a great distance. The other proof of concept of Oumuamua is Povehi, the black hole at the center of M87. So again, Uncle Larry worked with the discovery team here in Hawaii and named it Povehi, the adorned fathomless dark creation. And so this Ahua Hea Noa project, we see it as a language project where astronomy is the input. We are able to provide new and interesting objects with characteristics that then lead to the naming. Naming in Hawaiian language is an art. Coming up with the name Povehi, the adorned fathomless dark creation, as Dr. Jess Dempsey, the director of the East Asian Observatory, said, is that Uncle Larry summed up this object in one word. And it took 6 research papers to actually sum up what we're seeing with Poveghi. These are not the only 2 objects named. We have 6 objects in total named. 2 were named by Hawaiian Immersion School high school students, and the other 2 were named by a cohort of their teachers, their kumus. You can follow CFHT on social media. We are on Twitter, Instagram, and Facebook. Weirdly, most of my PIs I find them on astronomers on Twitter. So you might see a little bit more astronomy-centric content on that one, like updates on what we're doing that is really PI-centric, like call for proposals. We try to post at least once a day, every day. It's managed by myself and one of our remote observers, Callie Crowder. This is our staff. The pictures that are circled are Canadians. I have them circled because I use this same picture in a presentation when I talk to Canadian groups. So I like to point out they're Canadians. I mentioned that I had talked to 3rd graders just before this. We're actually running a self-guided solar system walk right now in Waimea through next Tuesday for the next week. We started it in mid-March. So what we do annually is actually, and I'll talk while I have all of this on the screen. What we do annually is set up a solar system walk from the Keck Observatory headquarters to our headquarters, roughly a mile. And we set the planets up to the scale that we would see within safety reasons. It really breaks my heart that I can't have them exactly where they're supposed to be, but I can't have kids get hit by cars, and that's more important. And so, the kids walk through, they have their passports, they go through, they learn a little bit at each planet about the contributions of the Mauna Kea observatories to our understanding of the solar system. They come to us, we are the Kuiper Belt, Pluto in the Kuiper Belt. And we have a barbecue. We usually have a costume contest. There are prizes. We couldn't do that this year. So we held our costume contest virtually at Halloween. We do this usually the Saturday before Halloween. And what we decided to do was have that same concept, but set up on a walking path that's a mile long. And it starts at the sun, and we have decals and with a QR code. And that QR code links you to a video that you can learn about that object, both in English and Avella Hawaii, which is, like a variety of different facts. The videos are really targeted towards elementary school students, their parents, the general public. So they're short, about 2 to 5 minutes. Some people were chatty and had a lot to share about their planet. And this entire walk is actually something that can be done remotely. So if your astronomy club would be interested in doing that, we have all of the materials in the future that you could print out the decals that we have, and the QR codes linked to our videos. And it's something that's really very easy to package and distribute for anyone who would be interested. So as part of a socially distanced field trip, I walked a 3rd graders through that today. We are currently in Hawaii in a blended learning mode at a lot of our elementary schools, which means that I don't walk them through once. I have to do the A students and the B students. So my calculations are I have walked to date 8 miles this week through the solar system. 8 miles in total through the solar system. If you do some math, billions and billions and billions and billions of miles. And so we just basically walk the kids through, and while they complain about the walking, what's really striking is when they're going from like Saturn and Uranus to Neptune, it really clicks in their brains. Like, this is far. Our solar system is way more spread out than textbooks would lead you to believe. So that's the end of my presentation. I'm absolutely happy to take any kinds of questions that you may have.
Thank you so much. So gentlemen and ladies, got any questions?
I don't have any question, but I've got to say it was a fantastic presentation. I enjoyed it very much.
Thank you.
Thanks for putting it together for us.
Definitely. We have 4 people here at my household watching you, so got my kids involved. So,
well, you know what? I was going to ask. I mean, I guess this is obvious, but all the observing with those telescopes up on Mauna Kea, they're all for deep sky research. You're never looking at the moon or anything like that.
I'm going downstairs, okay?
Or planets.
Actually, no. We do a fair amount of, and have the capabilities to do a fair amount of planetary research. So collectively. So for example, the NASA Infrared Telescope facility, they can look at objects in our solar system. I myself have imaged Saturn using them with some high school students. So a lot of the facilities can do that work. They can do it in different wavelengths. So I mentioned that I'm going to have a student who has KEK time. That student's actually looking at Io and has some questions about that in our inner solar system. We have observed the moon with CFHT on 2 occasions. One when L-Cross was crashing into it with our infrared camera. It's really about tricky in the optical, but when we think about the infrared and microwave capabilities, it opens up a whole kind of whole new world. One of the really concrete examples that I can give you is Venus observations that occurred in 2018 using the James Clerk Maxwell telescope. So this group of astronomers decided that they wanted to look at phosphine in the submillimeter as a biomarker, potential biomarker indication. So they decided, all right, proof of concept, we're going to look at Venus. We're not going to see any phosphine. They looked at Venus and saw a lot of phosphine. And so that led to some follow-up observations with ALMA. And so what they hypothesize is they've either seen a new geological process that we were previously unaware of, or microbe farts, because phosphine is in fact a biomarker. I have learned that penguins actually emit an incredible amount of phosphine in their penguin poop and their meat, which makes penguins very difficult to eat. And so that's an example. Now, lots of astronomers are doing follow-up observations of that. There is some questions of, was that an anomaly? Was it part of the data processing? So it's very much a hypothesis at this moment, but it's a really good example of the facilities on Mauna Kea doing stuff in our solar system, in addition to the obvious deep space work that they do.
I'm also interested in that one comment about the student doing research on the habitable zone of Agol.
Yeah.
Wonder how that's going to go, because I've been observing that, one of the more prevalent variable stars.
Yeah, she has her first. So what she wants to do is look at it in and out of transit. So we have some data of it out of transit for her, and she'll be getting some data in transit, I think in July, the next time that it's observable, from one of the LCO sites. Her most recent data is from Israel.
oh, wow.
Yeah, there's a whole LCO is part of a large global network. So
It's amazing. I wish our countries get along better as a science community. So, anybody else have any questions for Mary Beth before she leaves?
Yeah, I have one. Mary Beth, do the astronomers at the telescopes use information and things from, let's say, Hubble or the upcoming James Webb telescope?
Absolutely. A lot of the work that the larger telescopes and CFHT do is part of like those follow-up observations. So James Webb is a really good example of that. James Webb has a very specific science goals, science missions. We at CFHT will likely get a fair amount of follow-up observations with Spiru on some of the planets that are discovered by James Webb, or the inverse. If interesting planets are kind of go through that TESS Kepler pipeline, they're confirmed to be interesting using CFHT or KEK or something like that, then we can winnow those targets down to get a good, clear target list for Webb. It can also go in the opposite direction. So you discover something interesting with Hubble. Hubble has a very small field of view compared. So you might need to have a larger field of view, or you might need to integrate longer or do spectroscopy or look at it in a different way. So that's when kind of the data goes down in aperture, or like space-based to ground-based, or ground-based to space-based. There's an incredible amount of research that comes out of that combination of the two. Very few papers are published, particularly now with Gaia and its very precise positions. There's a lot of Gaia data. We have an entire survey that's devoted to Euclid. So Euclid is a European Space Agency mission that's going up, and they are limited in their wavelength. So we are actually looking in the R band. If you're familiar with the Sloan Digital Sky Survey bands, we're looking at the R band and the U band to basically, they don't have U-band capabilities. So we're looking at the R-band where they have those capabilities to create a reference there so that the data will run from the near ultraviolet all the way through whatever infrared wavelength they decided to take Euclid to.
Excellent. Thank you very much. Good job on the talk.
Thank you.
Yeah, I get the feeling you've done this talk before.
Yeah,
You did it so well.
It's as Paul can attest, it's identical to the talk that I gave in Pittsburgh. I do update it. So like if you had seen this talk 6 months ago, you would not have seen AU-McB in it. That's a recent discovery. And a lot of the stuff that I have with MegaCam, what I really like to impress upon with MegaCam is the legacy value of it. About 50% of our publications come from archival data. So when I go to the American Astronomical Society meeting, we have a booth, graduate students walk by, and they'll be like, oh, I use your data. I'm like, oh, that's fantastic. Do you want to talk about how you can get more data? They're like, no, everything I need's in the archive. So our archive is publicly available. It's at the Canadian Astronomical Data Center, the CADC. Anyone, you all can go and download any data that's not in the proprietary period and use it for whatever you're interested in.
Nice. Cool. Well, Mary Beth, if you can return host mode to me, you can pop off and I'll talk to these guys and we'll close up. Thank you so much.
Hello. I hope that's the right word.
Thank you.
It is. All right. Make host. I think I've made you host there. All right. Well, thank you. Enjoy the rest of your meeting. And I'm hopeful that you will be able to meet in person soon. So mahalo.
Yes.
Have a great
Definitely.
meeting. Bye.
Bye-bye.
Bye.
Bye.